So far, in our discussion about probability distribution, we have only considered discrete cases, such as the number of heads from 2 coin flips. Given this probability histogram, what is the probability that the number of heads from 2 coin flips will be 0? 0.25, because that is the value our column stops at. What about the probability of getting 1 heads? 0.5, because again, that's where the height of my column stops. What is the probability of getting 1 or less heads? Well, it would be the sum of the heights of these two columns, so 0.75. And what would you say is the probability of getting 1 or more heads? Well, now it would be the sum of the heights of these two columns, which is 0.75. Okay, last one. We need to sum these two heights, which is 0.5. Notice also, if I add up all these heights together, I get 1. This is a property that is true for all probability histograms. Now what I want to do is help you think about probability in a different manner. I want you to think about the probability of each column as the area of each column. Remember, to calculate area, we must multiply height times width. So the probability of 1 heads occurring is the height of this rectangle times its width. If I take the area under all the columns in my distribution, what should I get? They should always add to 1. Because we are dealing with discrete probabilities, we have taken some liberties and made the width of each column 1. We do this in place of using their actual real number value. See, if I make the widths representative of their actual values, then the width of each column would be centered around their numbers 0, 1, and 2, and they would all have a measure of 0. If the width is 0 for each column, so is the area and therefore the probability. So we make this continuity correction of expanding our column's width to avoid everything from being 0. For continuous cases, however, we do not make any such corrections, since there is an infinite number of values in any given range. So the probability of an exact value occurring is actually 0, since the width of its column is 0. For instance, the probability of a random number generator picking a real number between 0 and 100 is given by this distribution. Then the probability that 55 will be the number generated is 0, since the area of the column is also 0. What is the probability that the number generated is 97.365? For the same reason as before, it would also be 0. This can be very confusing for students because though the probability of the number being picked is 0, it does not mean that it is impossible for it to occur. If you think about this for too long, you'll drive yourself mad. But if you really want to understand this, you'll have to take much higher level math classes. What we can do with a continuous distribution, though, is calculate the probability of some inequality. For instance, I can find the probability of the number generated being 97.365 or less by taking the area of this rectangle. To take the area of this rectangle, we are missing one critical piece of information. We don't know the height of this rectangle, but we can figure it out. Remember what the sum of the total area should always be. It should always equal 1. This means that the total width of my rectangle times the total height of my rectangle should always equal 1. Then I can solve for my unknown by dividing 100 from both sides. Thus, the height of this rectangle is 1 over 100. Then the probability that the number generated is less than 97.365 is 0.97365. Before we do another example, I want you guys to know the technical term for a continuous probability distribution. that has the same probability for all values of x. We call this a uniform distribution, and its shape is always a rectangle. Let's try another example. Before we do anything, we must first find the height of this rectangle. We know the width of this rectangle is 1, and the total area must also be 1. Then I can find the height by dividing both sides by 1, and conclude that the height of this rectangle is 1 as well. So this rectangle has a height of 1 and a width of 1. Therefore, this probability distribution is actually a square. To find the probability that x is greater than 0.75, we must find the area of this rectangle. The width is 0.25 and the height is 1. Thus the area and the probability is 0.25. Given the following uniform distribution of wait times at a doctor's office, what is the probability that a patient has to wait between 2 and 4.5 minutes? We can find the height to be 1 over 5. Then the area of this rectangle is 0.5. Therefore, the probability that someone has to wait between 2 and 4.5 minutes is 50%. There is another commonly used distribution that calculates the probability of a continuous but non-uniform data type, and it's called the standard normal distribution. We know that a normal distribution is a histogram that is bell-shaped, and where the mean is located at the peak of the curve. Also, the horizontal axis is represented by some random variable, usually x. A standard normal distribution has the same components, except the horizontal axis is represented by z-scores, and the mean is equal to 0, and the standard deviation is equal to 1. I'm going to repeat this because it's so important. A standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. We will be working with this for the rest of the semester, so make sure you understand this topic. Because we are dealing with continuous random variables, the probability of our random variable equaling an exact value is 0, just like before. However, we can calculate the probability of ranges, such as from 0 to 1. To find the area under the curve, you'll need to find the definite integral of the probability density function. So hopefully you've been brushing up on your Calc 2 skills, because they're about to come in handy. I'm joking. In order to avoid computing the integral every time, statisticians have created a z-table, which tells you the cumulative area to the left of some z-score. For example, if you look at our z-score table and go to 0.00, it is matched with the value 0.5. This means 50% of the total area under the curve is to the left of my z-score 0.00. If I look at the number associated with the z-score of minus 1.86, it is 0.0314. This means that 3.14% of the total area under the curve is to the left of the z-score of minus 1.86. Notice how the ones place and the first decimal place can be found on the left-hand side column, while the second decimal place can be found in the top row. If I want to find the z-score associated with 99.2% of the total area under the curve to the left, I search the chart for 0.992 and find the associated z-score, which is 2.41. If I want to find the z-score associated with 49.2% of the area to the left, I find the value 0.492 on my chart and then use the edges to find the z-score. If I want to find the z-score associated with an area of 94.6%, to the left of my z-score, I search my z-chart, but the closest I can get is 0.9452 and 0.463, which have a z-score of 1.6 and 1.61 respectively. So what I do in this case is take the average of the z-scores. What if I want to find the z-score associated with 0.791 area to the right? Well, if 79.1% of the total area is to the right of my z-score, then 20.9% of the total area is to the left of my z-score. So I look for 0.209 in my table and find the associated z-score. What if I want to find the z-score associated with 28.43% of the area to the right? Well, if there's 28.43% area to the right, that means there's 71.57% to the left. Therefore, the z-score we are looking for is 0.57. What if I want to find the area to the right of 2.12? Well, if the area to the left is 98.3%, then the area to the right is 1.7%. What if I want to find the area to the right of a z-score of minus 1.4? Well, 8.08% of the total area is to the left. That means 91.92% of the area is to the right. What if we want to find the area between a z-score of minus 1 and 1? Well, the area to the left of a z-score of 1 is 84.13%, and the area to the left of a z-score of minus 1 is 15.87%. If I take away the area of 15.87 from 84.13, I am left with the area between minus 1 and 1. What if we want to find the area between a z-score of minus 1.95 and 0.23? If I remove the area of 2.56, I am left with the area I am looking for.